We're going to talk about carbon today, and there's a couple of terms we need to look at. Organic versus inorganic. This does not have to do with the vegetables you buy at the grocery store. Organic for us is just going to mean carbon, contains carbon. When you get to college, you'll hear about people taking organic chem versus inorganic chem, and it has to do with compounds that living critters use as well. Vitalism was a belief that only living critters could produce organic compounds. I wrote organisms. Only living organisms can produce organic compounds. Mechanism was the belief that all natural phenomena are governed by physical and chemical laws, and that organic chemicals can be synthesized by organic compounds, by inorganic, organic chemicals can be used to make organic compounds. And these are your three guys. Wohler here was the first to make urea. This was like 1828. And then you have Herman Colby with acetic acid. And then Stanley Miller. And this is 1953. And he demonstrated the possibility of organic compounds may have been able to be produced under chemical conditions of early Earth. And I'll have a handout for you. Talks more about his little setup, and we'll jump on that in class. So carbon. Carbon is looking for someone to bond with. I want you to pause the video and try to draw carbon, where the electron configuration. You should have something that looks like this. And if you remember from chemistry, your outer valence can have 8 electrons here. And so you have open spots here, 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 and here. This guy can make more bonds than anybody else, right? The column he's in on the periodic table. So up to 4 bonds. This is called, for us, tetravalent. Dang it. Sorry about that. Or that's typed right here. Having 4 possible bonding sites there, you're going to have carbon's going to be much more likely to make covalent bonds. Let me make sure I didn't write that somewhere. Covalent, which again means sharing. Nope. Unlike ionic, where you're transferring, carbon's not going to be likely to make ionic bonds. This tetravalence makes large molecules possible. And the 4 major elements of organic molecules are carbon, hydrogen, oxygen, and nitrogen. Carbon skeletons can vary in length, shape, number, and location of double bonds. When I say shape, I mean straight or branched chains, or these rings here. This variation in carbon skeletons contributes to the complexity and diversity of organic molecules. Hydrocarbons are molecules containing only H and C's, hydrogen and carbon, hydrocarbon, right? Major components of fossil fuels. Fossil fuels are produced from the remains of organisms that lived millions of years ago. They are not prevalent in living organisms. Hydrocarbon chains are parts of fats, and they are hydrophobic and nonpolar. Same thing, right? Hydrophobic. Yeah, baby. Isomers are compounds with the same molecular formula. Same molecular formula, but different structure and therefore different properties. You can see these guys here are C4. I don't know why I wrote 5. I said 4. C4H10. You have 3 types of isomers. Structural isomers differ in the covalent arrangement of the atom. The number of possible isomers increases as carbon skeleton size increases. They may differ in location of a double bond as well. Geometric isomers result from double bonds not allowing atoms they join to rotate freely around the axis of bonds. And you have subtle differences that affect biological activity here. In enantiomers, notice I wrote that O in. Make sure you write it correctly. Enantiomers occur when 4 different atoms or groups of atoms are bonded to the same asymmetric carbon, and you get 2 different spatial arrangements. Usually one form is biologically active and the other is not. They're not going to test you anymore over the functional groups, but we still need to know them for the macromolecule section. So these are just small characteristic groups of atoms that are frequently bonded to carbon skeletons of organic molecules. They have specific properties, but just make sure you kind of know your amino group has nitrogen, sulfhydryl, obviously sulfur, phosphate, phosphorus, and then carboxyl is kind of like these two added together. Anyway, I think that's the end.